Good morning. Okay, I guess so this morning you had Mark talk about machine learning methods in general, and so the next section I'm going to talk about probabilistic methods in particular. This is me. I'm Gideon. I was a graduate here in 2006. I was a CLSP workshop participant in 2000, 2007. Those are kind of old photos of me hanging around the Hopkins website. The work that I've done most recently fits into three big categories: information extraction, large-scale machine learning, and semi-supervised learning. So just to sketch each of these, information extraction is the idea you have some unstructured text and you want to extract some facts from it and maybe build some kind of structured representation. Now this isn't like a syntactic representation like a parser, but this is like facts that you want to understand from the world, like a timeline or a little biography. Large-scale machine learning is kind of the idea that, you know, in practice you have these classification problems or other kinds of regression problems where you have billions and billions of instances and millions of parameters. How do you do learning efficiently in that kind of a space? And if it takes 18,000 hours to train a model, how can you possibly do that? So the answer is, well, you have to do it distributed, and then you have to also be a little bit clever about how you do that so you reduce network costs. But I'm not going to talk about either of those today. Really, I'm going to talk about mostly semi-supervised learning. And the goal of semi-supervised learning is to reduce the human cost of supplying training data. So when Mark was explaining things this morning, typically the setup in machine learning problems is you assume that there's some input to the system, which is a set of tuples, training examples and training outputs. But really, there's nothing that ever comes like that. It's always an interaction between a person who has a particular problem to build, a particular problem to solve, and wants to build a particular model. So thinking about the human in that context and how they can inject more information to the system in a faster way, that's what I'm going to talk about. And the theme in semi-supervised learning that I'm going to talk about today is this new model that I've been working on for a little while, which is called the generalized expectation criteria. And we've applied it to a family of probabilistic models that you might have heard of or you might be familiar with, called conditional log linear models. And so the structure of the talk is basically I'm going to talk about probabilistic models, learning in probabilistic models, and I'm going to talk specifically about the conditional log linear exponential model family, and then I'm going to show how to apply the generalized expectation criteria to this class of models. If you have any questions at any time, please feel free to raise your hand, stop me. I'm happy to answer any questions. Okay, so this again is the outline. So I'm sure many of you are familiar with naive Bayes. I'm going to hopefully do it a little bit differently than maybe you've seen before. And I'm going to talk about, in particular, maximum likelihood estimation. Then I'm going to go through conditional log linear models. Then I'm going to talk about the generalized expectation criteria as applied to these models. Okay, so again from this morning, this was, I guess in a vague sense, what Mark presented. This is supervised machine learning. You have some training data, these tuples, instances and outputs, and you estimate the model parameters theta. And then you learn some function, and the function maps a particular x into an output y. And then inference is simply the process of when you get a new x, you predict y. Okay, so there are supervised machine learning, two parts, training and inference. Or training is also called estimation. Inference is also called testing or evaluation. Okay, so this very, very general framework can be expanded in a lot of different ways. So you can imagine that x and y, well, what is x? X could be a vector. It could be a vector of binary values. It could be a vector of real values. X could actually be a matrix. I mean, maybe you could think of it in a computer as a vector, but maybe there's some more logical representation as a matrix. Correspondingly, y. Y could also be an integer. If it's a classification problem, then it's an integer. If if y is a real value, then you're dealing with a regression problem. Y also could have some kind of structured output. It could be itself a vector, so there are multiple components to y that you want to predict. The F, the model, is the model family, and that's, for any particular set of parameters that you might be searching over, you're searching within a model family F. And then, even within this framework, there are a lot of different questions. In particular, a crucial one is, how do you estimate the parameters? Okay, you have some training data, you have picked your model or your model family. How do you figure out what the best parameters are given your training data? And so one of the kind of the surprising, or maybe not so surprising things, is that for a particular model or model family, you might have many different estimation methods or training methods for that particular model family. So to give a very simple example, in basic statistics, there's the concept of the mean, which is the arithmetic average. But then there's also the median, which is the number which falls roughly in the middle of all the values. And there are different properties of both the mean and the median. And people have given empirical and theoretical justification for each of these. So, okay, today in this talk, to be particular, this is the things I'm going to talk about. I'm going to talk about classification. So here, y is an integer or a vector of integers, and x is a vector, or in some sense, a matrix, perhaps. The family of probabilistic models that I'm going to look at is, the family of models is the probabilistic models. Now, Mark covered a number of models this morning. He covered support vector machines, decision trees, nearest neighbor did he cover? So there are a lot of different model families that you can imagine looking at. I'm going to look at one very specific model family. And the estimation method I'm going to introduce first is the method of maximum likelihood. And so I think the reason that I like thinking about it this way, and what I hope that you get from this, is that it's very useful to be able to come up with a model description and separate that from the estimation method that you're thinking of. And being able to think about things flexibly, like in that kind of a framework, lets you approach new problems. And so when you're thinking about a new problem, you might think of, well, what's the model description that I want? And then attach the estimation method. And then in a lot of cases, people use estimation methods which are approximations to the model they want to learn. And so often something which seems very complicated to learn turns out to be simple to approximate. Okay, so here is an example problem. Document classification. So document classification is something that people have explored a lot in machine learning. I think primarily because it's very easy to explain and kind of present what the outcome that you want. And it's also easy for a human to annotate and to evaluate the output of a model. But here's the problem. You have two snippets of text. Text about, so in this case, it's baseball stories and hockey stories. So I don't know if you can read the text up top, but the top story is a story about the Mets, and the bottom story is a story about the Rangers. So the top is a baseball story, and the bottom is a hockey story. So here, just to give you something concrete to hold on to, I'm going to represent a document as a vector x. Each element in the vector represents a word in the vocabulary. So clearly the length of x, the size of that vector, is equal to the size of the vocabulary. And so for a particular document, that position in the vector has the value 1 if the word is present in the document. Okay, and now the output space, y, is in the space of 0, 1, where 0 represents a baseball class or 1 represents a hockey class. Now, this mapping of classes onto integers is arbitrary. You can imagine doing it other ways. One way that actually people look at quite frequently is y's in the space of -1 and 1. So in the case of support vector machines, thinking about the binary decision problem in that way makes the mathematics a little bit easier. Okay, so naive Bayes. Who, by a show of hands, who is familiar with naive Bayes? Okay. Can someone tell me what that first equation is saying? Or what the first equation is a trivial example of? Exactly. So naive Bayes starts because that's Bayes' rule. And so at inference time, how do you choose y? Well, you just take the argmax over all y's and the one which is predicted with the highest likelihood. Okay, and then so why is that next equation an independence assumption? Oh, okay, thank you. Okay, so here I said make an independence assumption. What's the independence assumption that's being made there? Yeah?
All the xi's are independent of each other given the class label y.
Exactly. So this is why it's naive, because you're saying all of these xi's are independent. Okay, so you put these both together, and now you have that the predicted output y is the argmax over all the classes in that equation. Okay, so that's naive Bayes. So, oh, okay, good. Why don't you need the px? So up here when I said we were going to do inference, I wrote it out like this, but I didn't write the px term. Why didn't I do that?
It's the same for all the output classes.
Exactly. So it has a probability. That probability is relevant if you care about that probability, but if you're just choosing the max, it doesn't matter because it's the same. Okay, so many of you have seen naive Bayes before. How do you estimate these probabilities? Or intuitively, what might you want those probabilities to correspond to? Exactly. Yeah. So intuitively, you want features which are more correlated with a particular class to have a higher probability of being generated by that class. Okay, so that makes sense intuitively. So now I'll show you something which I didn't see for a long time, which is how to actually derive that answer, that intuitive result. So it's going to be a lot of work, or a small amount of work, but I think it's worth it because it shows, all the steps that you could imagine going through for a new model family. Okay, so what are the parameters of the model? Okay, so here this is theta I y, which is a particular element in the vector, its correlation with y, the probability of that word being generated by that class. This is called the prior. That's just the probability of that particular class. Okay, now why are these constraints? Well, why do they need to be true? Exactly. So if you don't have these, then you won't get probability distributions. Okay, so now we have the model, we have inference, we've described what the set of parameters are. How do we get from this to finding a good set of parameters given some data? So a fundamental method in statistics and in machine learning by proxy is maximum likelihood estimation. Okay, so the maximum likelihood estimation is the concept that you find, or the set of estimators which find the parameters which maximize the likelihood of the model giving the training data. Okay, so what's the likelihood? So the likelihood it's the likelihood of a theta, and d is the data. And so kind of the emphasis here on this likelihood function is actually a function of theta. It's a function of the parameters. and the data is assumed to be fixed. So the idea is you're going to vary the theta, and that's going to change the likelihood function, whereas you're going to keep the data fixed. Okay, and the likelihood of theta is p of theta of d, where this is your model. And then you can expand that by saying this product. Okay, but wait a minute, what assumption is being made here when you go from the probability of theta of the data to just the probability on each particular data point of the output given the input? Oh, I like this thing. This is great. What assumption is being made in this step? Yes, exactly. So all the data points are being generated independently. Okay, and so this is the likelihood function. That's what you're going to maximize. But typically, actually, people use this. So they use log of x. And the reason is that you can actually see that the mathematics going to look a little bit easier. So instead of a product, you have a sum. And that sum just by itself means that gradients work out nicely, for example. Okay, so likelihood and log likelihood, those are going to be important steps along the way. Okay, so in this framework, the likelihood of the model is going to be called the objective function. And parameter estimation, so the next step that I'm going to talk about is really going to be a function optimization. So it's going to be maximizing the likelihood function, or your objective function, subject to a set of constraints. So again, remember, we've defined the model. We can calculate the likelihood for a given set of input, and we have the constraints, and the constraints that are necessary in order for this to be a probability distribution. So now, proving that calculus is actually useful. So here are Lagrange multipliers for constrained optimization. So you may or may not remember this from calculus, but this is the function you want to maximize f, subject to some constraints g. And the method of Lagrange multipliers says to maximize this function, which is f minus lambda g minus the constraints. And the theory says that if you maximize this, then you get a maxima of f where the constraints hold. Okay, so we still got some more work to do, but then we're going to get to kind of a proof of the intuitive result of why you should simply take the counts. Okay, so first thing that you do to solve this series of equations using Lagrange multipliers is you take the partial derivative. So here I'm just going to show you for the prior theta of y. So you take the partial derivative of that function with regards to y, and you get this. And you then take the partial derivative of that function with regards to length, and you get that. And then when you solve this system of equations, you can then derive the result that the count is the appropriate maximum likelihood estimator for the prior. So if you look at this is a sum over data, and this is a indicator function, which is 1 if that particular data point has the value y, and this is simply the number of documents. Wow, okay, so that was a lot of work. I mean, it would have been a lot easier if we had said at the beginning, okay, let's just do the intuitive thing and take the counts. But I think it's worthwhile going through and really taking the time to go through all the tiny little steps, because this is the kind of method that you will be able to use in order to solve new estimation problems for new models. And when you can describe new models, then you can apply it to more interesting problems, and you can really break new ground. Okay, so just to recap, here's what we did for this in general for probabilistic models. You defined a model and you defined the parameters. So this was our model. We defined that the probability of p of y given x is going to be defined to be the prior and then the product of the independent probabilities. And again, this is a approximation to what the true probability would be. I guess actually, since we left off the p of x term, this isn't even actually a probability, but this is approximately equal. And then we maximize the model likelihood by adjusting the parameters using function optimization techniques. And In this case, we were able to get a closed form solution where the prior was simply equal to the count over the number of documents. And if I didn't show you this, but you could use a very similar method and derive the same formula for the counts for the probability of x sub I given y. Okay, so that's the easy part. So now we're going to talk about, or I'm going to talk about conditional log linear models, starting with maximum entropy models, or also called multinomial logistic regression models. Okay, so the previous model was generative. Can someone tell me what does that mean, that it was generative? Or what that might mean. Yes, this is the clue. So in a generative model, you have this intuition that the data or the observed variables x are being generated by the labels y. So as opposed to some other methods which would directly model the output. So p of y given x, that's a discriminative model because you're directly predicting the y. And even though it's an underlying generative model, we used it in a discriminative context using this Bayes rule. So one of the consequences of using Bayes rule is that you're forced to model this prior. So even if you were going to say that there's a uniform distribution over y, that's still a model assumption. So the next set of models, or the next model family that I'm going to talk about directly or tries to directly model p of y given x. So I'm not going to go into it in a huge amount of detail, but just to give you a little passing familiarity, has anybody seen this kind of graphical model representation before? Maybe Jason presented? Did he? Okay. So here you have some hidden variable. These are the blank circles. And you have some observed variables. These are the solid circles. And this isn't quite right. But these are factors. And so they're functions of a particular configuration of a value of an observed variable and a value of a hidden variable. So here in this diagram, there's only one hidden variable with multiple observed variables. And the probability of so this is kind of a discriminative setup. So you have, you're predicting a y given an x, you're predicting output given an input, and it's going to be simply the product of all of these factors. Okay, so if this is one output and multiple inputs, what does this correspond to? Yeah. So yes, in that you could describe a hidden Markov model this way, but actually this is a little more general. This is describing generally any kind of a sequence model where you have multiple y's and multiple inputs. But yes, a hidden Markov model would look like this. So again, if you were in a discriminative context, p of y 1 given n given some x would be simply the product of factors, of all these factors. Okay, so maximum entropy models, also known as multinomial logistic regression models. This is their basic form. So you have the probability of y given x is equal to 1 over c of x times e to the sum of over k factors or features, theta k, psi k, x, and y. So, okay, there are a bunch of pieces. Let's do this first. So z of x is called the partition function. It's a normalization function. What does that value need to be in order for this to be a valid probability distribution? Okay, what are the, yeah. Yes. Yeah. Okay. Oh, geez, are these out of order? No, I just missed something. Okay, so I think this is what you're saying. So this is the sum over the outputs, the sum over e to the all of those factors. If you want a probability distribution, it has to have that value. Okay, so let's dig a little bit deeper. What is this psi k? Well, psi k is simply any function of a particular input and output pair. So if your input is a vector and your output is a class, it might be something like this. Psi of x and y is 1. That function is 1 when this particular vector parameter is 1 and you're looking at this class. So y prime is the class you're interested in. So in the case of document classification, xi is a particular word, and this parameter corresponds to this feature corresponds to a feature which is on when, say, the word is Mets and the class is baseball. Yeah.
So is there, like you also call these factors, is there a difference between factors and features, like conceptually even, or is it?
No, they're the same thing. Yeah. Okay, so given this definition, how many parameters would you need if you wanted to have each feature represented uniquely for each class?
Sometimes millions.
Millions. So if x is, if you have a vocabulary in the millions and you have 100 output classes, you need 100 million parameters. And you might conceivably have many, many more. Okay. So one way to kind of understand the name logistic regression is by analogy to linear regression. How many of you are familiar with linear regression? Okay. So you can, if you squint a little bit, you can kind of imagine that here what's happening is you're having a summation is over a number of inputs, but instead of a linear combination of those inputs, you have a logistic function. Okay. So maximum likelihood estimation now for maximum entropy models. This is the likelihood function, or the log likelihood function. And then here I just wrote it, I just kind of applied the log to every particular instance. So the way it falls out is this first factor is, these are the parameters or the weights, theta k, and these are the features or the factors, psi k. And then this is the partition function. And I kind of got a little bit lazy, I didn't write it out, but this is a partition function on some input data. Okay. So how do we optimize that? Well, I'm not going to use, or I'm not going to present Lagrange multipliers here. Instead, people typically use gradient-based optimization because it's not a constrained optimization problem, it's an unconstrained optimization problem. So here it's an iterative approach. You have some particular value of the function for some parameter settings. Let's see. So you optimize this function by taking the value at this point and moving it in the direction of the gradient by some amount.
Your x, you mean theta?
Yeah, I do. I don't know why I wrote x. Okay, yeah. So you have, thank you. So here you have a gradient on the theta parameters, the theta, and here you have the function on the theta. And so this is a little graphical depiction of the process that you might go through. So you have your initial set of parameters, x sub 0. You find the gradient, that's this arrow. You move in the direction of the gradient. You get to another parameter settings, x sub 1, that has a different value for that function, which should be either minimized or maximized, depending which you're way you're climbing on the gradient. You apply the gradient function again, and you take another step. And as you apply this, you get to a minima or maxima, depending, again, which way you're going. There are many types of gradient-based optimization methods. I'm not going to talk about any of them, except to say that there is a huge amount of work, and typically just understanding this is sufficient. So you have some kind of function you're trying to optimize using a gradient-based method, and to do it, basically you have to understand how to evaluate a function and how to take the gradient. Okay, so how do we do this for maximum entropy models? Well, the gradient is the vector, which consists of the partial derivatives with respect to each particular parameter. So this is the log likelihood of the parameters given the data, or condition on the data. And this is a particular parameter, theta sub k. And for that particular parameter, this is the value of the gradient. The gradient will actually be a big vector. Again, maybe millions or 100 million dimensional vector, where each position of that vector corresponds to this. So in the first part, these are typically called the constraints. So this is just the values of the feature for or the number of times that feature happened.
Yeah, the empirical.
The empirical count, yeah. And this is the expectation. So this is your model prediction times the feature value. So now that you have this gradient calculation, that's all you need for maximum entropy models. You have your model, you describe your set of parameters, you calculate at each step, you calculate the gradient, you give it to a gradient-based optimizer, you run a step, and you walk the path, and at the end you get a set of parameters. So actually this derivation was one of my Google interview questions. So I was very happy that I knew that. Okay, so this is naive phase versus maximum entropy. So this is a paper by Andrew Ng and Michael Jordan, 2002. So they have a paper comparing empirically and theoretically the differences between these two classes of models, which they describe as a generative discriminative pair, because they have kind of the same model structure, but one is trained generatively in a generative fashion, one is trained in a discriminative fashion. Okay, so this is the solid line is naive phase, and this dashed line is maximum entropy. And so you can see that actually when and this is data going from left to right, and this is error. So you want to decrease the error, and as you get more data, the error hopefully should also decrease. Sorry?
The x-axis is in millions? Or just the...
I don't think so, no.
I see an n.
Yeah, no. I think that's just the count, yeah. So, so you can see that as at the very beginning, for very few instances, naive Bayes has an advantage. And then as you get to more instances, pretty quickly maximum entropy models get to an advantage. And I think there are a lot of theories as to why this is true. Some of them include the concept that naive Bayes models, first of all, they make this independence assumption, which we know to be incorrect. And so even if they're able to be estimated robustly, the underlying model is flawed. So as you get more data, it's not even possible to represent, or you're not going to be able to find as good a position in the parameter space. Okay, so that wraps up my very quick presentation of maximum entropy models, and now I'll start talking about conditional random field models. So this is one sequence labeling task. It's a Craigslist apartment listing. You have some apartment listing, and you want to annotate each word with a label. Is this a feature? Is this a description of the neighborhood around the apartment, the size of the apartment, restrictions, or the rent, the cost of the apartment? And the goal is to annotate each word with a label. So this is one example sequence labeling task. Can someone, or could some of you please give me some other sequence labeling tasks you might be familiar with? Yep, part of speech tagging. Yep. So those are probably the two biggest uses of sequence labeling: part of speech tagging, named entity recognition. So in both of those, in this case and in those cases, one of the complexities of this type of problem is that some of the labels you only know from context. So like this slash. I mean, it's just a slash. You only really know what the meaning of that slash is, or the semantic context of the slash by the surrounding context. And not just the lexical items, but also the label assigned to the lexical items. So as opposed to a model which would have a separate classifier on each word and they would be unconnected, sequence labeling tasks usually benefit from some kind of model which makes a joint decision, usually. So here are conditional random fields. So up here, this is a hidden Markov model. So did Jason talk to guests about this a day or two ago? Is that right? Or not yet?
I don't think he went into much. I mean, he talked about it about.
Okay. Well, he at least presented the idea. So this is a hidden Markov model, and this is a conditional random field model. Okay, so there are a number of things different and similar in each of these models. So the similar thing is that they're both describing a sequence labeling task, a solution to a sequence labeling task. But, okay, what are some of the differences between the two models?
Is it dependency between the observed data?
Yeah, so that's right. So here, this function is a function over multiple input units, yeah. Whereas that's not modeled here. And the reason that it's not modeled here is that the independence assumptions that are imposed on the input doesn't allow you to model them appropriately. Okay, so that's one. Yeah?
Attacks need not to be probabilities.
Yeah, that's another good point. So here you assume that you have a conditional probability distribution. That's not assumed here. So what's the immediate consequence of that? So it's the partition function. So if the HMM doesn't need a partition function because you're multiplying these probabilities together, and so the entire space, the entire output space is not deficient simply by definition. But here that's not true. So because these are improbabilities and the weights could be arbitrary, now you need some way of making sure that everything sums to 1 and that you're constraining the space. Okay, so what we got? So the first comment was that there's some kind of correlation that can be modeled among the inputs. The next was that these aren't constrained to be probabilities. Let's see, is there anything else notable? So I think, sorry?
The model guide probabilities using HMMs and use condition probabilities.
Yeah. So here this is a joint model or a generative model because both are being generated. And here this is a discriminative model. So I stole this picture, as I stole a lot of different things from this talk. But this picture is really nice. kind of a framework that you can use to understand the differences between these models. So this is the naive Bayes model. That's where we started. The conditionally trained form is logistic regression, or the Maxent model. The HMM, in some sense, is an analog to the naive Bayes model. It's a generative model, but of sequences. Linear chain CRFs are a conditionally trained sequence model that are, related very closely to logistic regression. And then each of these, both the HMMs and the linear chain CRFs, can be generalized to general graphs. So actually, before we go forwards, so the other thing I just want to point out is that the structure of the model is very similar to the maximum entropy models. In fact, it really almost looks identical, except instead of having these features which are just features on the input and one particular output, they're features on the input and multiple outputs, and so you have multiple outputs in each factor or in each feature. But otherwise, the model looks the same, and so I think one of the appealing parts about the framework for me is that now we can use all the same machinery to understand how to do optimization in conditional random field, how to do parameter estimation in conditional random field models as we could in maximum entropy models. There are a few things that are a little more complicated, though. Okay, so just as in maximum entropy models, you optimize using gradient-based methods, and we can take the gradient in the same way. Here, the constraints are slightly different. I apologize, I switched notations. So this is f instead of psi. But the constraints are identical. The expectations, however, are very similar, but a little more complicated. So in particular, if you look at this term, so for maximum entropy models, this was just the probability of y given x. Here is the probability of two labels, yi plus 1 given x. So now this is a little more complicated to calculate. And the way to do it is to use analogy from forward backwards in HMM training, and you can see that this probability, or this, so again, this is yi plus 1. This is the same thing except t instead of I. This is just a function of three separate pieces. The particular transition you're looking at, so that's the factor between two y's, and then it's also kind of, this is everything before that transition, and this is everything after that transition. And so the probability of going over a particular transition, that's the joint probability of a transition given some input, is the probability of going over that transition and then also having gotten there and having gone on from there. And so if you're familiar with HMM training, you'll see this analogy, you'll see this form, and it'll look very familiar. Okay, so that's it for conditional log. That's it for conditional random field models. I guess I probably should have had some experimental results showing you that they do better, but I think they've been adopted because they do better and because they allow you to model dependencies on the input, which would otherwise be tricky to do given an HMM. Okay, so now we can extend the same log linear model to dependency parser. So, at this point, maybe, it's kind of getting to be old hat, because it's the same, you can see that it's the same model and it's just in all these different contexts. And I think, apart from slightly boring you, I think that that it is useful to see that, this is the general framework, and you can see all of these models fitting into this framework, and you can see how you might extend this framework to model other different aspects. Okay, so dependency parsing. So a lot of people have looked at dependency parsing. Probably the first generative dependency parsing model was Jason Eisner's in 1996, Kohling. And then since then, a lot of people have worked on it, including Klein and Manning. Recently, people have started to look at feature-rich discriminative models. One kind of very popular class is these trees which are built from left to right, one decision at a time. Joachim Nivra been looking at that. Those are really appealing because you can run them in linear time, which is useful if you have a lot of sentences to look at. And then other people have been looking at scoring entire trees. And so here the idea is, well, what if we could have a model which assigned some value to an entire tree? How would we do learning and inference in that? And we're not going to assume necessarily any process for getting there. All we're going to assume is that this model exists. And then we can think about how to do inference and estimation given that class of models. But you can kind of imagine that actually the generative models and also this class of model, the way that I'm describing them here is it's not focused on the model itself, but really the process in which you're creating them. So in particular, the generative models start with you have a root. The root generates a child hit. It generates a left child John, and then it generates a right child with and ball, and so on and so forth. But this doesn't describe a generative process. It just describes a score. Okay, so the point of this slide really is just to say that, doesn't this look familiar? So this is the same thing. So we have X is an input, and actually typically people in dependency parsing use part of speech tags. Y is a vector of parent assignments. So yi is the parent of the ith word. And then you have feature functions over possible edges. And so these are called edge-factored dependency trees because each feature is only over one particular edge, so between two words. And it says basically, is this label yi, is that the parent of this? Is the word at position yi, where yi is the output, is that the parent of xi given all of the input? Okay, and this is the model. And so you can see again, it's the same business. Here we have the partition function, and this is again simply a log linear combination or exponential combination of some features with a particular weight. Again, to torture you guys, I guess I changed the notation again. I apologize. Let's see. So I guess the first thing is, so Ryan McDonald, colleague of mine, showed that inference, or finding the best particular output, is equivalent to finding a minimum spanning tree in a graph, where the weights are just these edge factors. So this was kind of a very nice result because it said that if you assume this kind of edge factored model, now I can tell you how to get the best tree out of this model. So you don't have to assume any kind of generative process. You don't have to assume any kind of way that the tree was generated, but you can just look at the raw weights and then figure out the best tree. Okay, and so by this for, you can notice that I stole that equation from someone else. Actually, I stole it from Noah Smith and David Smith, both Hopkins grads. But the idea is that you can use maximum likelihood estimation for parameter estimation via gradient optimization, and the only thing which changes is that the expectations are a little more complicated. So this is the partial derivative of the log likelihood function with respect to some parameter k. And I'm not going to go into all the details, except to say that you can notice actually it looks very similar. So this is the constraints again, and these are the expectations, but these are more complicated expectations, but they're still, again, the expectations. And computing the partition function z of x is complicated, but Noah and David showed that you can use a form of the matrix tree theorem to build it actually very quickly, and then in that also allows you to compute the expectations. Okay, so what was the point? I think, again, it's the same model family, the same description of the model, the same method for estimation, but the details, the mathematics is a little bit different. Okay, so this is what we've done so far. Oh geez, okay. So we defined, so the first part of like all of the different methods that we talked about is we defined a model. It's either naive Bayes, maximum entropy, conditional random fields, or conditional random field dependency parsers, or log linear dependency parsers. Then I said, given some data, we're going to determine the parameters using maximum likelihood estimation. And the way that we're going to find those parameters is using optimization techniques. And I showed you two, Lagrange multipliers and gradient ascent. And gradient ascent was used for all of these log linear models. Lagrange multipliers were for the naive Bayes. There are other methods that people use. But if you're going to know two, those are good starts. And then finally, once you have those parameter settings, to make new inferences, to make new output decisions given a particular input, you can use two. Here are two things. I guess I didn't cover Viterbi. Hopefully Jason at least hinted at that the other day. But I did spend a moment talking about the minimum spanning tree. So again, I think the take-home picture is that there are three separate things you have to consider. One is what the model looks like. The next is how you're going to estimate the parameters. And finally, how do you use those parameters to make new inferences. Okay, so that was, in some sense, a very long background introduction to the next part that I'm going to talk about, which is generalized expectation criteria. And the point of generalized expectation criteria is that it allows you to use alternative labeling modalities. And you can apply it to this rich class of discriminative models, and again, fit using gradient ascent. So I'm going to use all of the tools that I introduced in the first part, but actually now it's going to be a different objective function. Okay, so typically when people present semi-supervised learning, this is the picture, or one of the pictures they use. So you have two labeled instances, the blue class and the red class, and you have a lot of unlabeled instances. So the question is, how do you augment your labeled data by using unlabeled data? So GE criteria are functions over model expectations. So as an important special case, and what I'm going to talk about, they can be formulated to encourage model expectations to match domain knowledge and allow semi-supervised learning. Okay, so this is generalized expectation criteria. So generalized expectation criteria is a function over a scoring function, some feature set f, or some feature f, and some model p. And so it's the score of the empirical distribution of x of your data, and then the model's distribution over y of that particular function. For semi-supervised learning, this is one of the setups that we've used pretty frequently. So you have the KL divergence between two things, domain knowledge, which is encoded in conditional distributions of, say, labels given a feature, and B is the expected conditional distribution of labels as estimated by the model on unlabeled training data. So this is the instance of GE that I'll talk about for the remaining moments. Okay, so it's the KL divergence between this domain knowledge and this expectation. And the idea is that you want to find models where the parameter settings, you find parameter settings in which the expectations match the priors or match the domain knowledge. Okay. So this itself is going to be the loss function or the regularizer or the objective function or the estimator that is going to directly penalize model deviation from domain knowledge. Okay, so again with GE, it's an estimation method and it can be used in all of these model families. And so I'm going to present, I guess, quickly using this estimation method for a bunch of different model families, for all the ones we've looked at, in fact, for maximum entropy models, for conditional random field models, and for dependency parsing. So the idea of label regularization is that if you have some prior understanding of the distribution, the relative distribution between the output classes, you can use that to do learning. So if you have this one label and this other label, so this is class blue and this is class red, and you know that this is the relative distribution of the classes, then perhaps this looks like a reasonable decision boundary and says everything to the left is the blue and everything to the right is the red. And so in training or in parameter estimation, you simply replace the log likelihood with the GE criteria. So here this is the objective function. You're trying to find theta star. That's the theta which maximizes the log likelihood. So that's maximum likelihood estimation. And this is estimation with GE. You're trying to find the theta star, which minimizes the KL divergence between your prior domain knowledge and the expectation over your data. So, pretty simply, I guess I should have had I should have written out KL divergence, but you can just think of it as squared difference between this is a probability distribution, and this is the expectation over all of the data. So it says if you have 70% of your input data should be in the blue class, on any particular sample that you get, 70% should also be categorized by your model as being in the blue class. And you could also imagine actually using a joint objective function. And so using both, that theta should be over both of those, not separately. But you want to find the theta which jointly maximizes that difference. So estimating using GE works the same way as maximum likelihood estimation, except the function that you're optimizing is different. So instead of optimizing the likelihood function, now you're optimizing the GE function. And the way that you do it is you take the gradient again of the GE term. So this is form of the KL divergence. So P log the expectation of the model, which I'm writing as Q. And then with a little symbolic manipulation, you can put it into this form. And this actually has a relatively nice interpretation. Q of theta is the unnormalized probability distribution. And so this part in yellow says that if Q theta is proportional to P tilde, then the gradient is 0. And that is really what you want, because you want the model to be perfectly optimized or at its maximum where the model is able to exactly match the label priors you've given. So there are more experiments, but these are a few. So in all of these, this is a logistic regression with generalized expectation criteria, and I compared it to naive Bayes and naive Bayes with EM, and another method I'm not going to talk about. But this solid line is label regularization, and you can see that it does better in virtually all the cases, except for this one. 3 out of 4 of the cases. And there are a number of reasons. Part of it is that the logistic regression function simply is that model family is a better model family than naive Bayes. And then also that EM as a estimation method has some quirks and often goes off in kind of odd directions. Okay. Let's see. So that was label regularization, where you had the input, which is a prior over some P of Y, but you could also imagine some kind of other domain knowledge. So in particular, you might imagine you have some knowledge that a particular class is likely given some feature in the input. So for document classification, baseball versus hockey, you can imagine that a person could sit down and say, well, I know baseball words and I know hockey words. So this is the kind of domain information that you might give to the system, as opposed to a person sitting down and marking documents, saying this is a baseball document, this is a hockey document. Instead, they're going to sit down and say, these are a set of baseball words, these are a set of hockey words. And they give this information, and so it's a marginalized conditional probability of a label given a particular feature. So this is what a little snippet of knowledge might look like. Domain knowledge, the probability that the label is baseball, that the output is baseball, given that the word pitcher occurs in text is high, 0.99. And the probability that the label is hockey, given that the word pitcher occurs in text, is very low. And then again, this fits pretty neatly into the GE criteria.
So in practice, do you ask people to estimate what they think these numbers should be? Like, do you actually use this, or do you count? Or?
We've tried different things. It actually usually seems to be enough for people to just say 0.99 and 0.01. You can get a little bit of gain by estimating those probabilities more finely, but just a push in the right direction is usually what you need. Okay, so we have this model. We're describing a new annotation paradigm. Then the question is, do the labeled features really provide benefit over labeled instances? Is it actually going to be quicker? So this is what we did. We presented users with words selected by LDA. There's latent Dirichlet allocation. It's an unsupervised clustering method, and users chose the majority label for a particular word, or they could choose to ignore that word. And then after they did that, then we asked them to do traditional instance labeling. And then with each new piece of information, either the labeled word or the document, we retrained the classifier. So I'm going to show you some diagrams. In all the diagrams, they look like this. This is accuracy, higher is better. This is labeling time in seconds. This is each dot represents either a document or a word. So this dashed line is GE, and this solid line is traditional instance labeling. And actually, I think we used entropy, a different semi-supervised method here, but the results are virtually the same. And then at some point, we ran out of words to give the user, so we stopped giving them new words. So at that point, we just continue the line. So these are a bunch of different experiments. And again, the dashed up here, this is all of the GE experiments. On the bottom, this is the traditional instance labeling. So I think what's really striking about this, and I didn't think it was going to turn out quite this way, but there's a huge gain right at the beginning. between doing the word annotation and doing the instance labeling. Really quite significant. And the amount of time that you have to spend to do this is on the order of like 10 seconds, 20 seconds. Now, one of the things that you'll also probably notice, and I guess I'd be negligent if I didn't point out, is that in the limit, though, the traditional instance labeling does better. So you can see that after you get a sufficient number of instances, that is better than just the word labeling. And you can kind of imagine why that's true. Each instance actually gives a huge amount of information as opposed to a particular word. Yeah, I think there are 20 news groups. I don't know if the baseball hockey is, though. Is that 20 news groups? I think the Med Space and IBM Mac is. Yeah. There's more, but okay. Okay, so I showed you for, this is for classification. So now I'm going to take the same estimation method, and I'm going to do conditional random fields, and then I'll do discriminative dependency parsing. Okay, so the type of domain knowledge for conditional random fields that I'm going to talk about is the conditional probability of a label for one token given a particular feature. And you could imagine in the conditional random field case different types of input domain knowledge. But I think for right now I'm just going to talk about this, and that's all the experiments that we have so far, I think. So again, just to remind you, this is a sequence labeling problem. And this is going to be the domain knowledge. And so similarly to the document classification, you have the probability of a particular label for a particular word, given there is some feature of that word, is going to be the domain knowledge. So for example, you might say that the probability that the current label is a feature, well, that was a terrible example, but like cottage or kitchen, given that the current word is kitchen, is 0.9. So now this kind of opens up a new way of doing labeling. You could imagine typically what people do for labeling in conditional random fields is they'll label contiguous sequences. So from start to finish, they'll label the entire sequence, and then they'll use that sequence for doing maximum likelihood estimation. But actually, you could do something different. You could label isolated tokens and calculate the labeled feature across the whole corpus. So for example, if you want to figure out the feature, if you want to figure out a distribution for kitchen, you look at the probability that y is equal to feature given that the word is kitchen in lots of different contexts and estimate that entire probability distribution. As with maximum entropy models, the GE is applied using gradient-based optimization. So I guess this is, again, the maximum likelihood estimation. This is the GE gradient for CRFs. It's more complicated. And basically it runs into, you have to derive a dynamic program to efficiently calculate these. But the time isn't terrible. It's like n cubed or thereabout. And the way that it fits into the general model is the same. You estimate, you calculate the gradient, and you use it in this gradient-based optimizer. Okay, so I looked at two ways of assigning distributions as domain knowledge. First I looked at only the majority label. So you count across the entire corpus the probabilities, and then you choose the majority label. And then you assign all the mass to that label, and then divide the remaining mass. And then I also looked at actually sampling. And so this would correspond to a person who's sitting down and labeling isolated tokens. There are other people who have looked at similar kinds of methods. This is kind of an EM-like framework. And this is, again, a EM-like framework for hidden Markov models. And this is the result. So actually the Chang, Ratnoff, and Roth work, which is a EM-based HMM model, does slightly better than ours. But for various reasons. So I think there's reasons to be enthusiastic. So for example, this is their pure model, and here they apply constraints at inference time to reduce the set of outputs they look at. So when you take away those inference time constraints, then we do best. And this is, we compare to a different method, and we do well. And then finally, just to give you another perspective, this is, we compared CRF training with CRF training with maximum likelihood over contiguous sequences to GE training over labeling isolated tokens. So this is the number of tokens that were used for training, and this is the accuracy. Again, higher is better. This solid line at the bottom is traditional instance labeling, and up here is labeling isolated tokens. And so this squared box is, we took 99 different words and estimated their probability across the corpus. And so you can see that again, there's actually a pretty big gain from doing that over doing traditional instance labeling. Okay, I don't have a whole lot of time. I don't want to keep you guys too long. So I'm going to go very, very quickly through discriminative parsing. But basically, I think the point that I want to make is, I think in parsing, I think there's the most evidence that linguists or domain experts have a deep understanding. And being able to have linguists directly input or give their understanding to a probabilistic model would be very handy. And so GE is one way to kind of facilitate that. And so we use GE in essentially the same way. Instead of a KL divergence, we use squared error. But again, we use numerical optimization to maximize using gradient-based methods. Again, the partial derivatives are complicated. I won't go into any of this. But I guess I will show you some results. Let's see. So this is kind of unsupervised dependency parsing on English. That beautiful teal line is the CRF with generalized expectation criteria. And then that purple line is supervised training of the CRF using maximum likelihood estimation. And the other lines correspond to other unsupervised models. And so you can see that actually with enough feature constraints, those are input domain knowledge, GE does actually quite well and surpasses the unsupervised methods. And I think the only other comment I want to make about this is that when you look at unsupervised methods, I think the question is always, what is the bias introduced by the system designer? So in the other methods that we compare against, Klein and Manning's and also contrastive estimation, Noah Smith's model, there's a lot of tuning that they did in order to get good performance, which isn't encoded directly in the model, but it happens in the way that they set up their learning problem. So I think one of the advantages of GE is it's very explicit about the information you're putting into the model. It really is just these domain constraints. So these are kind of the points that I want to make about GE, which is that labeling features or alternative modalities can be more efficient than instance labeling, and that you can use them for semi-supervised learning of discriminative models. Did you have a question?
Yeah. To what degree is the model affected by the choice of individual labels or the individual components of the instance? I feel like if you pick ones that are more discriminative,
yeah.
do better.
Yeah, so if your domain knowledge is not that informative, you're not going to find a good parameter setting. So you have to find, your expert has to know what they're doing. So in some sense, maybe that's a higher onus on the human doing the annotation task than you would have with instance labeling. Yeah, that's a good point. Okay, so this is the end, and I just wanted to go over kind of the points that I think are the most important, which are that this is, when you're thinking about building a probabilistic model for a new problem, these are the steps you want to go through. First, you have to define the model. You have to pick an objective function. I talked about, so the models I talked about were naive Bayes, maximum entropy, conditional random fields, and log linear dependency parsers. I talked about two objective functions, maximum likelihood estimation and generalized expectation criteria. Then you have to find the optimal parameters for that objective function via optimization. And I presented two methods, Lagrange multipliers and gradient-based methods. And then finally, you have to use those parameters to make new inferences. So actually, I didn't present the Viterbi algorithm, but that's one example, and the minimum spanning tree is another example. So I think hopefully this framework will give you some tools to use over the next few weeks. Okay, are there any other questions before I let you guys go? Okay, thank you.